Hello. Hi guys, good morning. Welcome back to the new video. Ki hal chal? I hope you guys are doing good. In this, we're gonna see a problem. Minimum obstacles to removal to reach corner. Now, in this, you are given a 2D integer array grid with having zeros or ones. Zero represent empty cells and one represent your obstacles. Now, you can move in four directions, which is up, down, left, and right. Simple four directions. We have to return the minimum number of obstacles we have to remove so that I can reach starting from 0, 0 to m minus 1, n minus 1. This is my start, this is my end. And again, these will not be having obstacles. Although you can remove from the upper left corner, you can move from the upper left corner to the lower right corner, and each cell represents, and again these all are given. And if you look at the constraints also, it is mentioned in the very end that these two cells, which is upper left 0, 0 and n minus 1, m minus 1, are actually 0, 0, which means they don't have any obstacles. So I have to tell what are the steps which I will choose. Now, if we see the example first, we'll simply see that I can go in any form. I can go like this. I have to remove two obstacles. I can go like this, remove two obstacles. I can go like this, remove two obstacles. I can also have more obstacles. What if I go like this? I'm removing three obstacles, which is not good. So minimum here, we can easily see it is two obstacles. So answer is two. And in next case, we see, okay, we start from here and have to here. One way is to reach here, but then I have to remove one obstacle. But if I go and traverse like this, I am removing no obstacle. Thus the answer is 0. Now, for few of you folks, when you read this problem, especially of a grid, you might end up thinking of DP. Again, it's not your mistake, but if you had solved the DP on grid problems, there's a very standard pattern in there. Obviously, you have to minimize the number of steps, obstacle to reach any specific place. But usually in these, you can move in three directions, and usually those directions are kind of going towards one path, which means in DP on grid problems, you were able to go to these directions and then move from there, right? And same way, okay, from here you could go to this section and move from there itself. If we apply DP on grid here, it will pass, but the same will not happen for this one, because obviously I am trying to go towards and finding the shortest path here. Now, if you see this specific grid problem, you will realize, okay, DP is not a good choice, but maybe graph is a good choice, because we had similarly done graph a traversal algorithm on grids also. Imagine that you have maqsad target to reach from start to end, and you don't have to reach two obstacles. Then is there possibly a path or not? In that situation, obviously you will apply a simple graph traversal on this specific grid, right? But the only change right now which we are having is, rather than simply going is it possible to reach or not, we also are allowed to remove some specific node or some specific obstacles. So how will we go about it? And that too should result in minimum obstacles removal. So we realized it's a graph problem. We realized we have to do some kind of a graph traversal here. But on top of it, we realized that we have to get minimum obstacles. Minimum obstacles. For that, we are here. Then I will have to go and choose a specific location I should move on to. Then I have these two options. I have to somehow say or assign the priority to something, which means to go here, it's not good. To go here, it is good. Same way, to go here, it's not good. To go here, it is good. What is that graph traversal algorithm in which you choose something? Okay, this is good, this is not good. This is having a higher cost, this is having a lower cost. For you to go on to this specific cell, incur a cost of 1, because as you go to this cell, you have to remove this. So this specific will incur a cost of 1. This specific will incur a cost of 0. You saw that I'm trying to go towards, I have assigned, you can say I have assigned a weight, and I'm like making this entire grid problem to a graph problem, which you usually do. But now also that to just make sure, okay, let's change the color to just make sure that we are in, okay, some light color, let's say pink. Okay, so to make sure that we are taken in like taking in consideration the actual weight which they are given or the cost which they are given, I have assigned a weight to them. Okay, this specific block, if I go onto it, it will actually incur a cost of 1. If, and this is empty, so it incur a cost of 0. I'm coming from 0, so 0 plus 1 gave a 1, 0 plus 0 gave us 0. Now we know, okay, this grid, we have these edges. I simply assigned a weight to these edges and tried to build a graph. So now it's a weighted graph in which you have to find the minimum cost. Obviously, it's a weighted graph in which the weight represents the obstacles. So I have to find the minimum cost or minimum weight to reach from start to end, which means minimum weight will indicate minimum number of obstacles removed. Thus, I will simply now can apply a shortest path, single source, shortest path algorithm with weighted edges is the best and the most intuitive is Dijkstras. I'll simply apply Dijkstras here. Dijkstras says nothing. Take a priority queue. In that priority queue defined by corresponding min heap, and the first argument will be its corresponding weight. So next I will go to 0 to reach here. Again, I will visit only one cell once, because as soon as I visit a cell, that should be the shortest path to reach that cell. So okay, here I got 1, here I will get 0. Same way, here I will get 0. Again, you saw I visited this, I visited this, I visited this so far. Again, I am taking only the shortest distance or shortest cost and only visiting that. And that's what priority queue or min heap does. Always take the shortest distance. Then take this, go on to this cell. 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 Okay, here also I would have gone. Here also I would have gone when I was here. And again, take this, go on to this cell. Take this, go on to this cell. Take this, go on to the cell. So minimum cost to reach was 0. As you see, I never visited these because I was always taking minimum cost, which was 0 always. For example, if we take this, it is always 0. It is always 0. So I take this, I go on to these cell neighbors. This is visited. Then minimum cost is 1 1. Both ways it is actually 1. So obviously take one of them. Okay, I took this. Then I have to go and here place a 2 and 2, but again still 1 is minimum. Okay, take this, go on to the next cell 2, right? Again, this is not infinity, this is already visited, so I will not visit it again, right? Then again, I can all the minimum are actually 2. As you can see, all minimum, this is 2, this is 2, this is 2. So obviously take one of them. Again, let's say if I take this one, so I will take this, I will go and put it here as 3, sorry, 2 itself. Like this is 2, so I'll put it as 2 because there is no obstacle as such here to put it. Again, for this is 2, I will try to put it here. Okay, it's 2, already a non-infinite value. If I go down, oh, it's an infinite value. Okay, put it as 3 because it's an obstacle. If it is 2, oh, sorry, it is already visited. 2 minimum, then put it as 2. So minimum distance to reach here was actually a 2. Thus, you can simply use a priority queue. Let's say it's exactly very same as what we did. So I have M and N, I have the specific grid. I went on to all the specific grid initialization and put it as infinity. Then I will start off and make a priority queue. It's actually a min heap sorted by your min heap. Like I have taken a integer array as an as one of the piece of my priority queue, as a node of my priority queue, and that will define as firstly the minimum obstacles, then its corresponding row, and then its corresponding column. Cool. In the very beginning, minimum obstacles for 0, 0 is actually 0 itself. So I'll just simply put that integer array into my priority queue. And I will also take this minimum obstacles as a new array, which I have defined as infinity, and assign grid value, which is 0 itself by default. Until my priority queue is empty, I will get the topmost node from the priority queue. I will get the obstacles, the rows, and the columns. If it has reached the end, simply return the obstacles. If not, then go to all the 4 directions, check the new row and the new column, check if it is valid, that new row, new column is valid or not. If it is valid, check the number of new obstacles which you would be putting if you will put there at that new grid and column, considering the old obstacles you had plus the new like the grid which you are about to jump at, if it is obstacle or not. So if it's obstacle, I will add a 1. If not, I'll add a 0. Then you will get the new obstacles for that new row and new column. Considering that cell is not visited yet, visit it, which means put that obstacle, minimum obstacle, as that new obstacle count, and also put that in priority queue. Simply keep on repeating this. Ultimately, obviously, will always be able to reach to m comma, like m comma n. So this you will never come here, but still, you will just simply put a -1. Considering you are simply using a priority queue in which you will be putting in max to max all the cells. So complexity will be O of m into n, which means all the cells log of m into n, right? Simply imagining that in priority queue you are putting in worst case all the cells, and space will be O of mn because you have made a new array minimum obstacles. Now, if I ask you, can you improvise it? You will say, Aryan, I don't think so, because obviously I have used Dijkstras, which is the best case scenario here. And to optimize it, in that yesterday's video, you told us that for shortest path algorithm, when we have weighted edges, we always have to use Dijkstras. We can only use BFS for shortest path if we don't have weighted edges. But have you ever thought why? Obviously, why we cannot use BFS when we have weighted edges is because for weighted edges, I always have to take an edge, or I'll always have to take that specific edge which will give me minimum cost, right? In this case, I know that, oh, I have two possible options. I could have a grid, I could not have a grid. Now, in any which ways, if I have a grid or not have a grid, can I distinguish between them? Because again, that's a bit tricky to think of, but I'm just trying to make you think of possibilities, what worse could happen, or if we can do something out, because it's a new concept which I guess we don't see much often, and actually it's a very good concept to actually know. So the entire drawback of of like why we have to use Dijkstra's and not BFS is because BFS makes us sure, okay, at this level I'm putting in all the nodes here. I'm putting in all the nodes here. And again, you just put it in the queue and then you get it out from the queue and then you try to go to the distance and then again you put it in the queue and then get it out. The entire issue in this scenario is that your your cells which are having a lesser distance versus the cells which are having a higher distance both get mixed up. So can you do something that they don't get mixed up? Yes. Imagining what if you would have used a simple queue and you would have simply tried your simple BFS, what you would have done. Okay, I have a 0 here, right? Then I'll simply push that again. Simply imagine this as a queue. Here it is front, here it is your back or the end. So I'll simply push my this node. Let's say I number it as 0 comma 0, 0 comma 1, 0 comma 2, 0 comma 1 comma 0, 1 comma 0, 1 comma 1, 1 comma 2, and then 2 comma 0, 2 comma 1, and then 2 comma 2. Now I'll simply put a 0 comma 0, right? Okay, I will put it here and then I will visit its neighbors. When I say visited, which means this will go out, this will go out, neighbors will be visited. So next I will put 0 comma 1 into my queue and then 1 comma 0 into my queue. Okay, I put them. So this distance will become 1, this will become 1. Again, I will try to go that, okay, I removed this 0 comma 1, I will put its neighbors. So 0 comma 2 and put it as a distance of 2 and then 1 comma 1 and then 1 comma 1. Again, they put the distance as 2. So you see, okay, it's actually building up. Maybe we can use BFS, but this is building up just because of the fact that DP would also work here in this example. But again, still, I'm just for your simplicity actually building up this. So for this 1 comma 1, again you will try to go here. Oh, it's already having the value 2, which is not infinity, so you will not go here. You will just simply go here by removing this 1 comma 0. You'll simply put a 2 comma 0 in the queue itself, and then again this would simply keep on going. For example, next time you will remove this, you will put it here 3, you remove this, you will put here 3, you will remove this, you will not put here anything. Sorry, this is 2. And then next time you remove this, you will actually put it here too. This worked. Simple BFS worked. But again, simple DB would also work here. When this will not work, let's see. So again, this was 0. You put, again, I'm not just putting in the queue right now. Just imagine that this is actually a queue here, which we will be having. You will simply put a 1 and then a 0. The worst part about Q is it doesn't take weights into consideration, and that too, if I should more be specific, it doesn't take into consideration the amount of efforts or the cost which we'll encounter. Next time, the BFS will happen from here. So like I pushed these two, these like this is gone. I pushed these two into my queue. So this will be putting up 1, this will be putting up 2. So you realized ideally here I should have put a 1, but I put it as a 2 because I tried to actually start traversal. Basically in my BFS, if I just put it as it is a 0 comma 0, it is a 0 comma 1, it is a 0 comma 2, and let's something, and then 1 comma 0, then 1 comma 1, and then 1 comma 2, and then 2 comma 0, and then 2 comma 1, and then 2 comma 2. So I simply in the very beginning, front, back, I put it 0 comma 0. I removed it, then I put 0 comma 1 and then 1 comma 0. Then again in the next iteration, I will remove it, then I will put 0 comma 2 and 1 comma 1. You see, that's the biggest issue. You should have never tried to go from this cell to its neighbors because this is having a very high cost, having cost of 1. Rather, you should have used this as first, and this is actually where the priority queue helps us. Oh, it always chooses the minimum cost 1. How I can leverage my BFS concept here? Obviously, I will have to distinguish between the ones having the weights, the ones not having the weights. How I'll do it? Let's simply bifurcate and say that, oh, rather than having this queue with back and front, let's divide it. Anything which is good, I'll put it in the right side. Obviously, see, in a queue, you keep on pushing things, you remove it from the right. So I know the ones having these non-empty cells are having actually good, like they are actually good. So it's always good to push element here, right? To push element here. So what I will do in this scenario is that let's go back and then put it as infinity, 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 infinity. I'll simply, again in the very beginning, 0 comma 0 is in my queue. I'll remove it out from the queue. I have to go to my neighbors. Now this is actually an obstacle. It, as it is obstacle, I will push it in my back. I'll push it in my back. If I push this in my back, I'll simply say 0 comma 1 is pushed in my back. Okay, distance is 1. Now 1 comma 0, oh, push it in the front. 1 comma 0. You see, I pushed in front. With this, it actually came out. Oh, it actually came out to be okay. Now it is good. So it is now 1. Okay, sorry, it is now 0. Now, if I will actually remove it, I'll remove from the front itself. I'll remove from the front. Oh, I removed it from the front. Then again, go to its neighbors. 1 comma 1. Oh, 1 comma 1. Push it in the back. 0 to like 2 comma 0. Oh, 2 comma 0. Push it in the front. It became a 0. Then again go on to zero's neighbors. Obviously, remove it. So I'll remove it. I go on and put it as 2 comma 1. Oh, 2 comma 1. Okay, put it as 0. Again, remove it. 2 comma 2. 2 comma 2. Remove it. Oh, remove it. Then okay, let's say 2 comma 2. Sorry, 2 comma 3. 2 comma 4. 1 comma 3. 1 comma 4. 0 comma 3. 0 comma 4. Cool. Then simply at 2 comma 1, remove this. Put 2 comma 2 comma 3, 2 comma 3 in the back. This became a 1, and your 1 comma 2 in the front. Same way, remove this and put 1 comma 3 in the back, and your, again, this has become a 0, this will become a 1, and this will become a 0 again. Put 0 comma 2 in the front, and thus keep on repeating this. If I show you the same case again, This is simply nothing but 0, 1 BFS. Good ones at the front, bad ones in the end. Even if good ones are exhausted, then you will start using bad ones, but still the queue order is maintained here also. So what you will do, let's see here in this case that how bad ones are handled, because this is already everything is good. So it seems very simple, but let's see how the bad one will be handled. Let's remove this and let's see how you will do it. Okay. So initially in the very beginning, 0, comma 0, put it here. Then both are bad. So 0, comma 1 and 1, comma 0, both are put up here. Okay. 1 and 1 distance put up here. And then obviously this is gone. Next time you will remove from the front of your front of your queue. Obviously you have to push it, like you have to get it from the front, you have to push it from the front, you have to push it from the back. Thus you cannot use a you cannot use a simple queue. You will have to use a DEQ. But coming on back to the dry run, we now removed a 0, comma 1. What you will do, you will simply push its neighbors. 0, comma 2 is pushed, obviously it is 2, and then pushing 1, comma 1 also. 1, comma 1 also pushed it as 2. Again, remove your 1, comma 0. You remove your 1, comma 0. Neighbor, oh, already not infinity, so it is already visited. Don't touch it. And then 2, comma 0. Okay, 2, comma 0. Put it. Okay. Then this becomes this, like this became a 2. Again, you get out 0, comma 2. You get out 0, comma 2. You get out 0, comma 2. I got this out. Then its neighbor. Oh, it's empty. Ah, this was making sure I'm visiting blocked cells in the order of when they were visited first. And things being visited first indicates they are good, or they are visited, because see, it's BFS, breadth first search. Think visiting first is actually a good thing. The only thing here is that also have obstacles. So the ones which are not having obstacles should be given a priority. So it's 0-1 game. The ones not having obstacles given a priority. The ones having obstacles can be having their own BFS going on. I realized that 0, comma 2, if I visited 1, comma 2, oh, this is empty. So it should be given a priority out of all these, because all these, if I removed right now 0, comma 2, it indicates everyone else in its back will be having a cost equal to or higher than him. So obviously in that case, I should be good in this terms. That okay, I'll put 1, comma 2 here. Then okay, but okay, he has no other cells, which is neighbors. 0, comma 2 is gone. Next time, this is again a value of 2. Next time, I will put it from the front itself. So I'll remove 1, comma 2. Oh, I'll put 1, comma 2. I'll put 2, comma 2, and I have reached the end. That's value of 2 cost. Thus, now that is the reason you can actually use your simple BFS here. This is called as 0, 1 BFS because 0 here and 1 here. Imagine, always remember why you are able to use BFS here is because anything which is on the right side of this portion of Q will have a lesser or equal cost than anything on its left side. It's just that considering if you got an empty cell, your cost might remain that much, your cost might remain that much, but still you should try to traverse or exhaust your empty cells so that you can reach your final destination. Cool. Let's see the code. It's exactly same. Firstly, exactly same input initialization. The only thing is I now used a DEQ. I simply add the same thing, the corresponding grid 0, 0, 0 and 0. Then until my DEQ is empty, get the current, get the corresponding obstacle count. If it is your target, simply return the obstacles. If not, then try to go to all the 4 directions, go to the corresponding, find the corresponding next row if that is a valid row column, and also it is not visited yet, then simply make sure that if it is a obstacle, put it in the end, which means I will simply assign firstly the obstacle +1, because obviously +1 is because this is actually a grid having obstacles, and also make sure that put it in the last of your DEQ, else put it in the front of your DEQ. I'll simply put it in the front of my DEQ and thus ultimately get my answer. Make sure why this works to put it in the front of the DEQ is because, again, because see, in a normal queue, you always put it in the back, and that works because putting in the back defines that anything in the front will have a lesser or equal cost than anything before. But in this example, putting in the front worked because whenever we encounter an empty cell, the distance never increase, that the actual cost never increase, because that cost is not based on distance, but it is based on obstacle. I'm again referring, go and watch all the words I mentioned of why we can use BFS here, because don't even think of using this kind of BFS in normal approaches where you can replace Dijkstras. This is very standard just because of when you move on to empty cell, your distance never increases. So on empty cells, there is no relation itself in empty cells, which means on the right side, there is no relation itself at the first place. Thus, you are able to put on the, like, you are able to put in the front of your DQ itself. Cool. I hope you guys got it. And again, if you have any doubt whatsoever on any clarifications, questions, just go and watch the last part of the video, which I have told you, in which I have mentioned that why you can use a BFS like BFS, and not like, again, as a benefit of priority queue on top of elsewise of a priority queue. So again, as we use a simple BFS, the time is O of m into n, because you are visiting every cell exactly once. Because every time in priority queue also, in Dijkstra's approach also, and this approach also, I made sure that I'm visiting a cells which are having not visited ever. I'm only visiting those cells, and ultimately the space is O of m into n. Cool. I hope you guys got it. Again, the fact here, the problem is simple, but the fact of you knowing about using a BFS itself is actually a very big stuff. And again, many people get confused into DP. That's the reason I told about DP also. Bye bye. Take care. Do follow us on Twitter and Discord and Telegram. Bye bye.